In the name of Allah, the most gracious, most merciful. Hello everyone, this is Dr. Tariq Masood. Thank you very much for watching my videos and your wonderful support to make this channel a grand success. We are a partner and family. Please subscribe and share our channel if you haven't done so far. We as a team can work together to convert our challenges into opportunities and opportunities into success stories. These success stories can be monetized into value addition. Thank you very much again for your precious time. Okay, today I'm going to discuss my lecture number 2, Smart Grid Control and Operational Challenges. How the STATCOM, SSSC, UPFC, SVC, TSSC, TCVR, how they're functioning. Before my lecture, I used to read a Quranic verse. Rabbi shrah li sadri wa yassir li amri wa halul uqdatam min lisani yafqahu qawli rabbi zidni ilma. Okay, now from next page I'm going to run a complete trail on my lecture number 2 on smart grid. Okay, smart grid operations and control challenges. Introduction, lecture number 2. Okay, from my next slide I will give a brief about my future plan and then I will give you key takeaway points of my lecture. Okay, the understanding of the facts, concept and technology. So we have planned to deliver 100 lecture on facts technology on smart grid basically. So we will start from facts technology concept, power semi-connected devices, voltage source converters, self and line commutative current source converters, SVC and STATCOM operations, static series compensators, static voltage phase angle regulators, combined compensator UPFC, special purpose fax controllers, and application will demonstrate a couple of application fax devices implemented in United States. What we going to deliver after implementing fax technology, shaping the global energy delivery, fax and resolving gridlock, and delivering clean and poor power energy in the world by large. Key takeaway points, lecture number 2. So what are the key takeaway points from lecture number 2? First, a power system infrastructure development, and then we'll talk about a power system complexity. Then we will discuss reactive power, significant and management system. Okay, dedicated to faculty members and student, particularly leadership, VCs and teens. So I've been visiting this university frequently every year. Okay, smart grid evolutionary development. What are the key factors or driving factors and influence to implement a smart grid or smart approach? First are external factors, then operational factors, and grid conditional requirement. Okay, now on my next slide we will give a brief about what are the external factors, operational factor, and grid condition and requirements. Based on that, what are the issues, what are the challenges, and what are approaches available to implement in order to improve the system operations performance. Okay, fundamental approach for smart grid operational challenges. What are basically these challenges are? Okay, now first grid condition and requirements, second operational factors, and number 3 external influence. Okay, in grid condition and requirements, variable power supply. So we have variable power supplies. Number 2, integration of distributed resources, increase distance between resources and load. Number 3, operational factors, greater transmission network complexity, aging infrastructures and lack of experts, high power delivery quality. Number 3, external influence, legal and regulatory framework, integration of renewable energy resources, CO2 reduction, and energy efficiency. In order to synergize these factors and to deliver the quality, what we have to do as far as the smart grid is concerned. So we need complex grid structures for as a smart solution. Okay, what we have to do first? as we mentioned earlier, self-healing, then grid rapid detects, analyze, respond and restores, number first. Then empower and incorporate the consumers. So the ability to incorporate consumers' equipment and behavior in grid design and operations. Number 3, tolerant of attack, grid mitigate and resilient to physical and cyber attack. Number 3, provide a power quality needed by the 21st century's user. Based on CMBA curves, grid provides a quality power consistent with consumer and industry needs. Accommodate wide variety of supply and demands. Grid accommodate variety of the resources including demand response, combined heat and power, and photovoltaic and end user efficiency. Fully enables and supported by the competitive markets. That is the last. Okay, perceptive approach of electric power grid performance. Now we are going to discuss in the power grid performance. Transmission grid infrastructure development. What is basically demonstrated here? Extension of interconnected systems, number 1. Number 2, increase power exchange among the interconnected system. Transmissions of large power blocks over long distance lines like hydro resources, renewable energy resources, and favorable locations. That is the 4 factors. So these are 4 key elements must be developed in order to deliver a quality power. Okay, power system complexity here. What is basically? So in power system complexity, electromechanical system, when we are operating, if we had tripped 1100 megawatt power dip here, so the complexity resulted in a major blackout from time to time, affecting millions of people and a loss of large generating power. Okay, if we consider in United States, August 2003 power dip is happened, and February 2008 complete blackout. Okay, now we are going to discuss what are the 3 or what are the main key parameters who make the power system complex. First thing, power flow. Second is called stability, and third, reactive power management. In a power flow, normally we are facing 3 issues. Number 1, uncontrolled power. Number 2, a power loop. And number 3, unbalanced power flow. In stability, we have different type of stability issues. Rotor angle stability, frequency stability, voltage stability. In the rotor angle, a small disturbance angle stability and transit stability. In voltage stability, it will be a small disturbance voltage stability and large disturbance voltage stability. Okay, and in reactive power, we have 2 mode of operation, and the capacitive mode of operation and inductive mode of operations in reactive power management. Okay, what basically its dimensions here? Power flow are not optimally controlled, first challenge. Number 2, reactive power, reactive reserved and need to be managed. Number 3, system stabilities are not fully controlled. Number 4, inadequate training for planners and operators. Number 5, lack of effective data integration and information exchange. So these are 5 hot issues which need to be addressed in order to address the complexity or complexity attributes. In first, what is attributes? Power flows are not optimally controlled. Second, reactive power need to be managed. Number 3, system stabilities are not fully controlled. Inadequate training of the planner and operators. Number 5th here, lack of effective data integration and information exchange. Okay, AC power transmission system limitations. Okay, what basically it demonstrated? First, uncontrolled power flow. If we have uncontrolled power flows, its results are what it demonstrate a low power transfer capability, bottleneck and loop flow. Now if you can see here, this is my power flow schematics, uncontrolled power flow schematics. Some areas are fully loaded, some partially loaded, and some area even though there's no power flow. Now I will discuss here a bar chart which show my network. This is my network here, how it's operating. If you see here, in my bar chart, line 2 and 3 are showing almost 100% loaded, and line 4 and 5 show only 25% loaded. Okay, and 2 and 4 line, again it is almost 50% loaded. So 1 and 2 80% loaded, and 1 and 3 almost 70% loaded, and 2 and 5 here almost again 70% loaded here. So it's mean this my network has a lot of unused capacity. In order to, this is my 4 and 5 and 2 and 4 and the other areas. So in order to convert unused capacity into a fully utilized capacity, we need a technology or reactive power management system. So from my next slide, we will demonstrate how the reactive power is playing a significant role in order to fully utilize our power network operations. Okay, consideration of reactive power to maintain seamless AC power transmission operation. Okay, now the first thing, I'm going to AC power transfer system. What is basically? The real power transmission is measured into megawatt and reactive power measured in MVR. Okay, if you can see here, this is my conductor here. It has a two-state. One is electrostatic field function V, and second has electromagnetic field function I. What is basically this is known as a capacitive reactive power compensation behavior. It's called the electrostatic field function F. And second, this is also known as the inductive reactive power compensation behavior, electromagnetic fields. So this is my compensator, how it's functioning on capacitive and inductive mode of operations, both sides. Okay, now surge impedance loading, SAL, is a function of V, L and C. So over here we can calculate how much the surge impedance should be there. On my next slide, I'm going to demonstrate the relation between load and surge impedance, how the capacitive and inductive mode of operation is contributing in order to maintain a seamless AC power system, transmission system operation. Okay, in the how to manage the reactive power at different load based on surge impedance load. If you can see the first scenario here, if the load is greater than cell, it's mean light load condition. Capacitive is greater than inductive. This may lead to a over voltage. If you see here, this is my capacitive is greater than the inductive, so it can cause a over voltage. Now number second here, load is equal to SEL, surge impedance. It means load is equal to surge impedance loading. So capacitive is equal to inductive here. Power transmission system has not been utilized properly. Okay, so if both are equal, then it's mean power transmission system has not been utilized properly. Okay, number 3 here, third condition scenario, load is greater than cell. When load is greater than surge impedance, it's mean load is greater to cell surge impedance. So the inductive is greater than capacitive. This may lead to voltage instability. If we have a capacitive if the inductive is more than the capacitive, then it can create voltage instability. Okay, now in the first scenario, if capacitive is greater than inductive, then it's mean over voltage. Number 2, if capacitive is equal to inductive, it's mean transmission network is not properly used or fully used. Number 3, if inductive is greater than capacitive, this may lead to a voltage instability. Now you have a 3 condition in front of you and 3 challenges, and know where we should run or where we have to operate our networks, and a capacitive mode of operation or inductive mode of operation. This is up to you. First here, maintain a smooth and uniform voltage profile. Important. So deficiency in reactive power will cause voltage to drop, surplus will cause voltage to rise. Very important, we need to understand. Okay, surplus reactive power will cause voltage to drop or surplus will cause voltage to rise. Number 1. Number 2, reactive power supply is essentially for reliable operating the electric transmission system. So inadequate reactive power leads to a voltage collapse, has been a major cause of several recent major power outages worldwide. Number 3, reactive power can also substantially increase a transmission capacity and improve efficiency of the real power delivery. So it's mean the reactive power is playing a key role in order to deliver seamless power system operation. Okay, how to manage reactive power in electric power system? First here, so the generators can either generate or absorb reactive power, supply reactive power when overexcited and absorb it when underexcited. Reactive power capability curves determines limits for production and absorption of the reactive power by the generators. First is the generators. Number 2, overhead lines can also provide or absorb reactive power depending upon loading. When loading is above SIL lines, absorb reactive power. At loading below cell, then they produce VARs. So that is how the system is performing. Number 3, transformers always absorb reactive power regardless of the loading. Number 4, underground cables generate reactive power loaded below the SI limit. Surge impedance loading. That is a 4 area which are playing a key role in order to utilize the reactive power. Okay, so how to manage reactive power in electric power systems? So the power generators. So during normal operation, the generator will produce reactive power when the machine is running in an overexcited mode of operation. Number 1. Number 2, alternatively, generator will absorb reactive power when the machine is running in an under excitation mode of operations. Nevertheless, the amount of reactive power generator or consumed by the generator is totally depending upon the generator performance curves. So this totally depends on the generator performance curves, how much you need to generate or how much you need to absorb reactive power. Okay, now conclusion, what we discuss? We have discussed a power system infrastructure development, power system complexity. We have discussed a power system limitations and a reactive power significance and management systems. That we have discussed 4 topics. Okay, on my next, this topic still continue. We will discuss further on reactive power management. Okay, these are a few papers I have just linked here, references. First, my papers I have published in there is a large number of papers published. This paper is published. First is a 2017 Second paper published in 2013, then 13, and then 2007, and the other books. These are 4 references I have attached for your further study. So you can find on IEEE, or you can Google and find these papers. Thank you very much. Thank you very much for your precious time to make everything possible. Please do not hesitate to send me your feedback and commerce.masood.dr@path.edu. Please stay at home, stay safe, inspired, and blessed. Thank you very much again.